Is it on or?
Joel says it's good.
Say it again. I couldn't hear.
I think it's working fine.
Okay, good. Okay, I guess let's get started without delaying things much. Okay, I don't see the room, but it's okay. Welcome, everyone. Today, as we discussed, we're going to have a research lecture. We're going to cover 4 cutting-edge papers from our group on topics that we have covered in past lectures so far. And the first 2 are on in-memory computing and DRAM, and the third and fourth papers are on genome analysis acceleration, and third one is on in-storage computation. But you will see that all of these papers merge memory and computation in some ways. So the first one will be presented by Ataberk Olgun. Ataberk is a PhD student in my group, and he did this work while he was an intern and also a master's student. He got his master's. This is master's thesis, essentially. He's going to present a new way of generating random numbers at high throughput using a previously unknown mechanism in DRAM chips. Ataberk, please go ahead.
Thanks, Onur, for the introduction. So I'll present our, before I start, I will hide you so that people can see the.
Yeah, that sounds good. And I would suggest these talks, each talk, including Q&A, hopefully will last for at most 40 minutes so that we can cover all talks and have a break in between also.
Yeah, I'll try to finish it fast.
Okay, but take questions also. So that's the purpose of these talks. Okay, go ahead.
Yeah. Again, thanks for the introduction. I'm kind of excited to present this for the first time in person. I'll be presenting QUAC-TRNG, high-throughput true random number generation using quadruple activation and real DRAM chips. This paper was published in ISCA 2021, and it's a collaborative effort from researchers from Safari and Kasırga Research Labs from ETH Zurich and Toby University of Economics and Technology. And we have a collaborator from University of Toronto also. I'll start with an executive summary. We're motivated by the fact that we can use DRAM to generate true random numbers at low cost, and we can provide this functionality to many devices that exist today. However, when we look at the existing DRAM-based true random number generators, we see that they're either based on fundamentally, they exploit phenomena that are fundamentally slow, so they can only generate true random numbers at high latencies, or they cannot effectively harness entropy from a large number of cells that exist in a DRAM row, so that thereby they provide low throughput random number generation. And our goal is to develop a high throughput true random number generation, true random number generator that can also provide numbers at low latency, and that uses commodity DRAM devices because we want to benefit from the fact that it exists everywhere. And our key observation in developing this true random number generator is that by using carefully engineered command sequences, we can activate 4 DRAM rows by sending only 2 DRAM activate commands. And our key idea is to use QUAC operations to activate DRAM rows that are initialized with conflicting data patterns to generate random values. And we develop QUAC-TRNG based on QUAC operations. It is a true random number generator that generates random numbers at really high throughputs and low latency by repeatedly performing these operations. And we evaluate QUAC-TRNG using 136 real DDR4 chips. We show that we can generate true random numbers at throughputs going up to 5.4 gigabits per second per DRAM channel. It outperforms the existing random number generators by 15 times and their enhanced versions by 1.4 times. And it can generate true random numbers at very low latency. We can generate the true random number, 256-bit random number in 274 nanoseconds. And we evaluate its security guarantees, and we show that it passes all 15 standard randomness tests developed by the National Institute of Science and Technology. Standards, sorry, yeah. So this is an outline of my talk. I will start by explaining what true random numbers are. There are many ways to define randomness, but for the purpose of this talk, we will go with this definition, a sequence of bits without any discernible pattern. And when you look at these numbers that I put here, you can potentially figure out that these first two numbers look rather not random because there's a pattern that exists that you can see yourselves. And the last number here looks a bit random because there doesn't seem to be a pattern that exists in the bit sequence. To produce random numbers, we use what's called random number generators. And this can be a device or a program that will generate random numbers that will produce a random bit sequence. When we look at how they generate true random numbers, when we look at how these generators generate random numbers, we see two different ways of doing that. And the first one is pseudo-random number generators. So these random number generators will continuously operate on an initial value called seed. They will perform some arithmetic transformations to this seed and maintain a state internally. And a function of the state will be their output. True random numbers, in contrast, they will sample random physical processes to generate random numbers. From a cryptography perspective, pseudo-random number generators are less secure than true random number generators, simply because if the seed value is compromised, an attacker can potentially recover your random number sequence. But even if the attacker has access to your true random number generator, the only thing the attacker can do is to generate yet another random number that you didn't generate before. Okay. So one important aspect of true random number generators are their quality. And we need to find a way, we need to have a way of discerning between low quality and high quality true random number generators. And to do that, we use what's called statistical tests. These tests evaluate various statistical properties of true random numbers that our generator generates, such as the number of proportion of logic 1 bits in the bit stream, for example. And based on the number of tests and based on how well your generator passes these tests, it will either say that your random number generator is high quality or low quality. So where are random numbers used? High quality true random numbers, they're useful for many applications today. One of them is cryptography. In cryptography key generation and signature generation, we use them. In simulations, scientific simulations, we use random numbers to provide certain simulations with numbers that belong to a certain distribution. And even in ML, we use it to perform randomized training, or we use it in genetic algorithms. Yeah, so true random numbers can only be obtained by sampling random physical processes. And unfortunately, not all computing systems today have these devices that we can use to generate random numbers to sample physical processes. And this limits the platforms where we don't have too many resources. We cannot fit many more resources into there to sample random physical processes. Basically, it shrinks the application space of random numbers. But when we look at DRAM, we see that it's ubiquitous in modern computing platforms. It exists everywhere. And TRNGs that are based on DRAM can generate true random numbers inside DRAM chips. And this is particularly useful for these constrained devices, such as your mobile phones or even smaller boards, because it doesn't require specialized circuitry to generate true random numbers. And they also can provide true random numbers at high throughput, and they enable applications that require high throughput true random number generation in these devices. And finally, another point is that these DRAM-based random number generators, there's very synergistic with processing in memory systems. These systems typically perform computation directly inside a memory chip, which improves the overall system performance by eliminating data movement. And random number generation in DRAM allows this PIM device to generate true random numbers within the chip. So it doesn't have to go off chip to reduce efficiency, to potentially retrieve less secure random numbers from an off-chip link that you don't trust. So it enhances the security and privacy of workloads that you run in PIM in your PIM systems. Okay, I'll continue with a brief background on DRAM. So typically, when we look at today's DRAM organization, we see a CPU with a memory controller. It will be connected to a DRAM module through what's called a DDR interface. And a DRAM module has many chips. And inside each chip, we have multiple DRAM banks, and they share the same chip interface. Inside the bank, we have multiple DRAM subarrays. And each subarray, we will have word line drivers and sense amplifiers. And inside a subarray, there are multiple mats. They're separated by word line drivers. And then inside the mat, you see the classic 2D organization of DRAM cells. They're placed in a two-dimensional array, and we call a row of DRAM cells a DRAM row. And DRAM cell looks like this on the right side of the figure, and we will take a deeper look at this. So we will see how we access a DRAM cell. In a DRAM cell, we have a capacitor and an access transistor. It has two components. A word line connects the capacitor to the bit line through the access transistor. And there's a bit line that connects the cell to the sense amplifier. And the bit line bar signal is essentially the inverse of this bit line signal. And the sense amplifier has an enable signal that we use to read the cell out. Okay, so this is a timeline of events that happen when we want to access the cell. So initially, the word line is pre-charged to half VDD. Sorry, the bit line is pre-charged to half VDD. And first we enable the word line to connect the cell to the bit line. And then the cell will start to lose its charge towards the bit line because the bit line has a lower voltage level than the cell. In this example, the cell started with a VDD voltage level. And then there will be a deviation in the bit line voltage towards VDD because it was half VDD. Now it's going towards VDD. And then the sense amplifier, when we enable it, will sense this difference and amplify the voltage of the bit line to VDD, essentially reading out the value in the cell. And this operation also restores the charge back to the capacitor because the capacitor is still connected to the bit line. We will look at DRAM operation at the coarser granularity. We will look at it on subarray granularity. So we have this subarray from the previous figure. And because we typically access DRAM cells in the granularity of a cache block, we have multiple cells packed into cache lines in this figure. So this shows a DRAM command sequence that we will use to access different cells in this DRAM array. First, we send an activate command to enable the word line. And this will also copy the word line to the sense amplifiers. And then once the word line is in the sense amplifiers, we can send read commands to read read data in cache line granularity. And when we want to open another row or access a different cell in another row, we first need to send a pre-charge command. This will disconnect the word line. So it will set the word line voltage to 0 and then pre-charge the bit line so that we can perform another access operation, another activate operation. And then later we can send an activate command. This will again copy the value to the sense amplifiers. Then we can read this out using read commands. Okay. Yeah. So key timing parameters here that we need to obey to allow correct DRAM operation is TRAS. It dictates the time we need to wait between an active command and a pre-charge command and the next pre-charge command to the same bank. TRP is also called pre-charge latency. It's the time that delay between pre-charge and activate commands. And that's it. Yeah. So now I'll talk about QUAC operations, quadruple activation. We make a new observation in this paper. we see that carefully engineered DRAM command sequences can activate 4 rows at the same time in a DRAM chip, in a real DRAM chip. So to do that, we first send an activate command, and then we send a pre-charge command, but we greatly violate the default TRAS timing parameter. Instead of waiting for 35 nanoseconds, we will wait for less than 3 nanoseconds. And then we send another act command after the pre-charge command, but now we also violated TRP timing parameter, and we again violated greatly. So we only use 3 nanoseconds of delay instead of the default 14 nanoseconds. So with 2 activate commands, we activate 4 DRAM rows. We also find 2 characteristics about these operations, QUAC operations. So QUAC can only activate a set of 4 rows whose addresses differ only in their 2 least significant bits. And to explain this, I have a figure here. You see 2 sets of rows here, rows 0 through 3 and 4 through 7. And their addresses, the least significant 3 bits of their addresses. So QUAC can only activate the set of DRAM rows with the same color in this figure, but it cannot activate these set of rows at the same time because their least 2 significant bits differ. Sorry, the third least significant bits differ here, 0 to 1. And the other characteristic we identify is the first and the second activates addresses must have their 2 least significant bits inverted. Again, the similar figure here, we have 4 rows with their addresses. So we can use the first row address in the first activate and the third row's address in the second activate command, and this will open 4 rows. Similarly, we can use these 2, the first row's address and the second row's address. So we basically target these rows with the successive activate commands, and we see that we can open 4 rows at the same time. One detail is basically if you reverse the ordering, it will still work. But basically, if you send the first activate to first row and the second activate to third row, it won't work. And we verify this behavior on real DRAM chips using our infrastructure. We show that this works on 136 DDR4 chips that we evaluated from one vendor. So to explain why QUAC works, we look at the typical hierarchical design that's employed in today's DRAM chips. Because the DRAM vendors are basically troubled with high density and performance requirements, these requirements push DRAM vendors to produce hierarchical organization in their DRAM arrays. And hierarchical organization in turn enables high density and low latency DRAM operation. So this is another figure, the same figure that I showed in the background. It depicts a DRAM subarray. And here you can see that a master word line in the hierarchical word line scheme drives multiple local word lines. Now you will be able to see, sorry. If you're looking at the DRAM mat essentially, and we have master word lines, and we have local word lines. Local word lines drive the word lines that I showed you in the previous figure that enable the access transistors. Master word lines select essentially which set of local word lines will get enabled. There is a circuitry that connects the master word line to the local word lines. And there are these select signals S0 through S3 that I show here that essentially determine which local word line will be enabled when you enable the master word line. So we will look at how these signals are driven and how it enables 4 rows at the same time. And this is our hypothetical row decoder design. It operates on the least significant 2 address bits, and it produces these select signals that I showed you in the previous figure. And it operates in essentially 2 steps. In the first step, it will pre-decode the least significant 2 bits, and then it will drive these control signals on the right. So first it will, on the left side, we have inverters, inverted versions of the address bits, and their own versions, like A0 bar is the inverted value of the address, the first address bit, and so on. And we will store these signals in latches. And on the right side, we have AND gates, 2 input AND gates that connect these intermediate signals, A0 bar, A0, A1 bar, A1, to the select signals. So yeah, we will send an activate, pre-charge, activate sequence and see how this enables all four select signals on the right. So first we send an activate command to row 0, so the least 2 bits are 0. And this will set the latches that drive the intermediate signals, A1 bar and A0 bar to 1. And in turn, that will that will drive the S0 signal because it's the AND combination of those two intermediate signals. Notice that the S1 and S2, the AND gates that drive S1 and S2 have partially set inputs, but because A0 and A1 are not set yet, these won't drive their corresponding select signals. So to conclude this slide, first activate command will drive a single word line. And then we violate the timing of the activate to pre-charge delay, so that when we do this, the circuit is disturbed so that the A0 bar and A1 bar will still remain open because we didn't give enough time to pre-charge circuitry to do the thing correctly. As I said, pre-charge command cannot disable these two latches because there's not enough timing. Then we again violate the timing parameters and send the activate command to the third row. And this will now set these address bits to 1. So we encoded 3 in binary, it's 1, 1. And then this will drive A0 and A1. Because A0 and A1 are also driven now, all the AND gates will drive their corresponding select signals. And the second act will activate the remaining 3 word lines in the 4 word line segment. Yeah, and after this operation, all 4 word lines are enabled. And that's why we call it quadruple activation. Now I'll describe how we develop QUAC-TRNG based on QUAC operations. First, I will show you how we generate random values using this operation. So on the left, we have a diagram that shows 4 cells connected to the same bit line on 4 different rows. And the even rows, the cells on the even row are initialized to logic 1, and the others are initialized to logic 0. Yes, and the bit line and the bit line bar initially are pre-charged to VDD over 2. So on the right, we see the voltage difference on the 2 contacts of the sense amplifiers. This is the difference between bit line bar and the bit line signal. It's initially 0. And there are 2 voltage levels that we need to, the bit line voltage needs to exceed for the sense amplifier to do its job correctly, to amplify the signal correctly. And we call it ready to sense voltage. So now we will send an activate command to row 0. This will enable the access transistor of this access transistor on this word line, and the cell will share its charge with the bit line. We send the pre-charge command shortly after, so that the cell does, so that the sense amplifier has not yet enabled itself. And then we send an activate command this time to row 3, and then this will enable all 3 rows. Because we have conflicting data patterns, this will take the bit line voltage further down, because we initialize the 2 rows with 0s and 2 rows with 1s. And at this point, the sense amplifier will be enabled. It will try to sense a voltage that's below the reliable sensing thresholds, VTH value. So this will, the random perturbations caused by random physical phenomena here will force the sense amplifier to either sample 1 or 0. Randomly. This is how QUAC-TRNG generates random numbers. And our key idea is to leverage the random values that we generate on sense amplifiers to basically use them as a source of entropy. Here we have 4 rows, the same 4 rows. We call this a DRAM segment because this is a segment that we use to generate random numbers. And we have a sense amplifiers that are connected to the cells on this row. First, we initialize the rows that as I showed you in the previous figure. And then we perform a QUAC operation on these 4 rows. And then this will generate random values on the sense amplifiers. Now, once we have these, we will read them out. So to do this, based on a one-time characterization step, we calculate the entropy of different cache blocks in this row. And I'll describe it later in more detail. And we read them. We read these 256-bit Shannon entropy cache blocks to generate a 256-bit random number. So to conclude, with each 256-bit entropy cache block we read, we generate a 256-bit true random number. Okay, now I'll talk about how we evaluated it. We experimentally studied both QUAC and QUAC-TRNG operations in real chips from SK Hynix using DRAM vendor, our DRAM testing infrastructure. This infrastructure allows us to send arbitrary command sequences to DRAM with arbitrary timing parameters, so we can execute the command sequences that I talked about. The metric we use to measure randomness is Shannon entropy. And how we calculate it is like this. And essentially, this is a proportion of logic 1 signals and logic 0 signals in the random bit stream. So we sample each bit line's Shannon entropy, each bit line using QUAC operations, and calculate the Shannon entropy after 1,000 QUAC operations. And the intuition is basically, if you have a bit stream full of ones, you will get a Shannon entropy of 0. And if you have a bit stream that has an equal amount of ones and zeros, you will have a Shannon entropy in between 0 to 1. And towards 1, you will get a more equal amount of zeros and ones in that bit stream. As I said, we do this 1,000 times and measure each bit line's Shannon entropy at 50 Celsius and nominal DDR4 voltage. We test 8,000 DRAM segments, so 32,000 DRAM rows in total from each module. And we use 16 4-bit data patterns. And so a 4-bit data pattern is essentially this. So if I'm talking about all ones, what I mean is I initialize all 4 rows with all ones. And if I have a data pattern of 1, 0, 0, 0, I initialize the first row with all ones and the remaining ones with all zeros. We calculate the cache block entropy based on Shannon entropy. So this is the sum of all bit line entropies in one cache block. So it's 512 bits in total. And we have 2 metrics that we will plot in the next figure based on cache block entropy. It's the average cache block entropy is the average entropy across all cache blocks in one module. And the maximum cache block entropy is essentially maximum of the cache block entropies in a single module. And this plot shows the maximum and average cache block entropy for different data patterns on the x-axis, and on the y-axis is the value. And these are these error bars are showing you the distribution across all 17 modules we test, or 136 chips. So we make one observation is that we see entropy varies with data pattern. And yeah, here we exclude the data patterns that don't result in significant entropy from this figure. So 0, 0, 0, 0 will produce no entropy. And we see that highest average entropy occurs when we use the data pattern 0, 1, 1, 1. And to explain this, basically, I showed you in the previous figure how QUAC worked. It activates the first row a bit earlier than the other 3. So the first row has more time to share its charge with the bit lines. And it has a higher potential to bring down the bit line voltage towards 0. So when you initialize the first one with 0 and the remaining ones with 1s, remaining rows with 1s, the rows that get activated together, the last 3 rows, they bring the bit line voltage towards VDD more closely than the other patterns. We also calculate segment entropy. It's the sum of all bitline entropies in a segment. And we do this to show the spatial distribution of entropy inside the DRAM chip across rows. So here we plot on the x-axis the segments, segment ID. So this is going from one end of the bank to the other end. And on the y-axis, you have the value itself. We plot 3 lines here. Unfortunately, you cannot see the error bars, but the average is, again, the average segment entropy across all 17 modules. M1 and M2 lines are representative modules that follow 2 patterns that we observe across all modules. So you see that segment entropy behavior is different for different modules. Here you can see in this rectangle, module 1's entropy goes down, whereas module 2's entropy goes up. And we see that the entropy increases towards the end of a DRAM bank significantly. Key takeaways from these experiments, we observed that entropy resulting from QUAC operations change according to the data patterns we use and the physical location of the DRAM segments. And we relate these behavior to systematic manufacturing process variation and design-induced variation effect. I refer you to the paper for more details on these. And we evaluate QUAC-TRNG's quality. So we run 2 experiments to measure its quality. First, we use QUAC operations to generate bit streams on a bit line. And then we apply some lightweight post-processing using the von Neumann corrector. Our goal here is to see if a single bit line can generate random numbers that are high quality. So we generate these bit streams and then we put them through NIST tests. And similarly, we test the quality of QUAC-generated random numbers when we use SHA-256 post-processing. And again, I will show you the results. We use NIST STS on both experiments to evaluate its quality. And then this is a table from the paper that shows you the p-values for the different statistical tests applied by the NIST test suite. And what this essentially shows you is that QUAC and QUAC-TRNG bit streams pass all NIST tests, so they don't have any discernible patterns inside of them. And you can check the paper for more details. Okay, finally, we will estimate QUAC-TRNG's throughput. According to this formula, SIB here is the number of SHA input blocks in the highest entropy DRAM segment in the DRAM module. And L is the latency of one QUAC operation in nanoseconds. So how we calculate SIB? I talked about these 256-bit entropy blocks. We find these blocks by looking at cache block entropies across the segment. And we find contiguous ranges of cache blocks where the sum of their entropy equals 256. So we will split a DRAM segment into multiple regions, multiple 256-bit entropy blocks based on this characterization. NL, we calculated by tightly scheduling the DRAM commands, activate, precharge, and activate commands required to execute one QUAC operation. And then finally, we multiply by 256 because it's how many random numbers we generate with a single iteration. We evaluate the throughput using 3 configurations of QUAC-TRNG. The first one is one bank. It uses a single DRAM bank. And the second one is BGP. It exploits bank group level parallelism available in DDR4 to achieve higher throughput. And then finally, RC plus BGP uses row clone in DRAM copy operations and exploit bank group level parallelism to initialize data faster and exploit DDR4's bank group level parallelism. And to do row clone operations, we basically, what a row clone operation does is it copies a source row to a destination row in a single subarray, in the same subarray. And to do that, we use previously described activate, precharge, activate command sequences in the Compute DRAM paper from Micro 2019. So this is a plot that shows you the QUAC-TRNG throughput for 3 different configurations on the x-axis, the maximum, minimum, and average across all modules. We see that we achieve on average 3.44 gigabits per second throughput per DRAM channel on average. And in DRAM initialization provided by row clone greatly improves the throughput of QUAC-TRNG. And finally, we compared QUAC-TRNG to state-of-the-art DRAM-based random number generators, DRANGE and Talukder's work. So DRANGE uses activation latency failures, and Talukder's work uses precharge latency failures. And again, we calculate their throughput by tightly scheduling the DDR4 commands required to execute their iterations. And we evaluate 2 versions of each of these works. The base version is as they were proposed, and the enhanced version is a throughput optimized version of both of the works, where we use SHA-256 to make use of the entropy as much as possible that they generate. And we assume a 4-channel DDR4 memory in this evaluation. So this shows you the throughput comparison for all the all the configurations we evaluated, QUAC-TRNG is using row clone here. And we use row clone in the other works wherever possible also. So we apply all the optimizations we do to them. And we see that QUAC-TRNG outperforms the best prior DRAM-based TRNGs by 15 times at a realistic throughput, 2.4 gigabits per second DRAM throughput. And it also outperforms enhanced configuration, the best enhanced configuration by 2 times at a futuristic 12 gigatransfers per second throughput. Okay, there are more in the paper. We have the NIST randomness test results that I briefly described. We have throughput latency comparison against other DRAM-based TRNGs that are much slower. So I didn't put them here. We have a system integration study where we evaluate how QUAC-TRNG can be implemented in a real system. We have a brief system performance study. We show QUAC-TRNG's throughput with concurrently running applications that occupy the DRAM bandwidth. So how much left for QUAC-TRNG to produce. And we have an area overhead analysis, only 0.04% of a contemporary CPU. And the memory overhead, we need to allocate some segments to produce random numbers, is only 0.002% of an 8 gigabyte module. We have sensitivity analysis. We look at effect of time and temperature on quarks entropy. We see that entropy changes with temperature, and entropy remains stable for at least up to a month. So you don't need to characterize every day, basically. You can wait. The characterization result is valid for at least a month. QUAC-TRNG is open source. What I mean by this is all the scripts that we used to produce all the numbers is open source in this link. And going back to the system integration study, we have a paper recently published in HPCA 2022, led by Nisa, Dr. Strange, end-to-end system design for DRAM-based random number generators that evaluate these aspects in much more detail and solve the challenges regarding how you can implement DRAM-based random number generation in real systems. And you can watch her talk, HPCA talk on this link. Okay, I'll summarize and end my presentation. So DRAM-based TRNGs can provide high throughput and low cost random number generation to a wide range of systems. And the problem with prior work is that they cannot produce random numbers at high throughput and low latency. And our goal is to develop a high throughput and low latency through random number generator that uses DRAM. And we observe that we can do quadruple activation in real DRAM chips. We use these QUAC operations to activate rows that have conflict in data. And based on those operations, we develop QUAC-TRNG that produces random numbers at high throughput. And we evaluate it using 136 real DRAM chips. We show that we achieve 3.4 gigabits per second average throughput per channel. QUAC-TRNG has low latency, and it outperforms existing DRAM-based random number generators. And it passes all NIST tests, so it's secure. Okay, thank you for listening, and I'm done finally, and I can take your questions if you have any. Thanks.
I have one question.
Sure.
First of all, it's a really nice master thesis. Congratulations.
Thanks.
Second, how you guarantee there is any guarantees for the DRAM manufacturer that by violating the requirement of accessing the chip, you still can maintain data for other applications in the same banks or even different banks? There is this kind of guarantees.
Yeah, so I guess you're asking if by doing a QUAC operation, are we manipulating any other data in the same bank, right?
Basically, it doesn't affect the ability for the DRAM chip for other applications in the system.
Okay, yeah, I can answer it in, I guess, 2 parts of my answer. So first part is, when you do QUAC, you're only affecting the DRAM segment that you're operating on. So you initialize 4 DRAM rows. You don't allocate any other data to those rows. You have to reserve it for QUAC-TRNGs used specifically, specialized to QUAC-TRNG, and no other data gets allocated there. So we have a memory overhead, but it's quite small when you have an 8 gigabyte chip. And then regarding if these QUAC operations will make the chip worse over time, as in reliability characteristics will change, we didn't observe anything regarding that, but it requires an extensive study. Does that answer it? Or okay.
I think partially.
Okay, yeah, we can discuss later maybe. Yeah. Any other questions?
One.
Okay.
So you saw in your slide that you found like 135 chips were able,
36,
yeah,
yes.
out of how much?
Those are the all chips we tested from one manufacturer. So we didn't observe this behavior on chips from other manufacturers. So these are from only SK Hynix. We tested Micron and Samsung DIMMs, and we didn't observe QUAC on those. But the Hynix chips we tested, we observed it in all chips we tested. And we tested only this many.
Yeah, because my question will be like, how hard is to find chips where you can perform it,
Mm-hmm.
and how you find it quickly?
Yeah, you look for the Hynix brand on your module. If you cannot see it, then you just go for it and hope that the market share represents the probability that you get an Hynix chips from your module.
I should say something over here. Maybe you can put me over there. But Ataberk, is the behavior you're observing fundamental, or is it just in Hynix chips? I think it's better to answer the question more scientifically.
Yeah. So I already.
I don't care, for example, as a scientist, if my current chips are going to all support this.
Yeah.
In science, we do research for 10 years later, right? Or 20 years later. So is the behavior fundamental? Is this something that people can support if they want to, or if they find benefit, like your paper suggests?
Yeah, I think that's correct, because it's fundamental in the sense that you can do this operation as long as you activate 4 DRAM rows at the same time, or maybe 2 or 3, right? So if you implement support for that in your DRAM chip, you already have high throughput true random number generation support. Yeah, does that make sense? Or
Yeah, I think it makes sense, but I think what I was also getting at is, why don't you observe it in Samsung chips, for example?
okay.
There's a specific reason why you don't observe it, I think. And
Yeah, can I say it here?
yeah, go ahead.
Yeah, so basically Samsung ignores the commands when you violate the timings. So if you send an activate command and then don't wait for enough time, we didn't characterize how long you need to wait. But if you wait for 3 nanoseconds, the other commands are ignored. So there's a circuit in those modules or chips that prevent users from violating the standard, essentially.
Yeah, and that's an important point, I think, because that didn't used to be the case in Samsung chips. These are more recent Samsung chips that are doing that. So I think if I have to speculate, I should say that it's being done so that people don't exploit this sort of non-standard behavior, which is not good. I think this is not a good mindset in general in the DRAM industry, in my opinion.
Mm-hmm. Yeah,
we have discussed this mindset in this class quite a bit, so I think people in the class may empathize with this.
Yeah, totally. Yeah, I agree.
Yeah, because there's no fundamental reason why they should really ignore that second activate, right?
Yeah, I assume it also adds some overhead on their end, because they have now specialized circuitry that checks for violations and timing. Exactly.
Yeah. So I think I think your and my hypothesis is that they're just doing this to hide what's going on internally in their chips. Is that correct? And we've discussed this before, so I'm putting words in your mouth, but it's because we've discussed this before. Yeah.
Yeah, I mean, if they have such an intention, why not? Yeah, makes sense for them to do this.
Okay. Yeah. Any other questions? Otherwise, we should move to the next talk.
My last one.
Okay.
So basically, the activation of 2 rows rely on the policy of memory controllers, right? So in a full system, you don't have that fine-grained control. That's you can control basically your memory controller to send 2 requests directly to different rows that you want, because maybe you can prioritize, for example, the send up for a different row, perhaps for a different thread in the system. And in such a circumstance, how you deal with it?
Yeah, so I acknowledge that you need a custom memory controller for this because of 2 reasons, right? The first one is what you mentioned. You cannot guarantee that your requests will be scheduled in the order that you expect them to. And the second reason is we violate the timing. So memory controllers today don't violate the timings, at least dynamically. So you can still have some configuration capability when you change your BIOS settings, for example, for certain timing parameters. I adopt this, but probably you cannot go down to 3 nanoseconds. You can reduce them slightly today. But when you do it, it's not dynamic. It's once you do it, you have to operate your whole system with those timing parameters. That means you do QUAC without wanting to do QUAC, or operating the device correctly and not doing QUAC. So you need some support from the processor vendors or the memory controller manufacturers to do this. But we described 2 ways of implementing that in real systems by changing how the memory controller works. And Dr. Strange paper that I mentioned describes it in even more detail. I think it's doable. I think it's much less costly than integrating another true random number generator, for example, to your system that is this fast. That makes sense. Yeah. And we evaluate this and the overheads of these in the paper. Okay, thank you everyone for your attention.
Okay, thanks, Ataberk. Now we can move to the next talk. But before I think we move on, while Rakesh is getting ready, I'll say that this sort of new observations on what DRAM chips are capable of are really important to understand the capabilities of memory chips. Because as we discussed earlier in the course, the memory chips are designed as memory chips. People don't normally think of them as random number generators or computation devices, but showing that they can actually, their existing chips are actually capable of doing so presents big advance in terms of merging memory and computation in a very tightly coupled way. So hopefully there's more to discover here that are, and hopefully we'll discover things that are fundamental. There's a lot of potential for research in this direction. Okay, I think with that, Rakesh, are you ready, or are you going to be ready soon? I couldn't hear you, but maybe you're muted or something. I don't think you're muted, but I still cannot hear you.
Can you hear me now?
Okay, it's better now. Yeah. Okay, so yeah, so in the second talk, Rakesh will present something that's kind of similar, except in a different type of memory device, in flash memory, in NAND flash memory. He will show how to do bitwise and OR operations in flash memory in a way that's similar to Ambit, but specific to flash memory. Rakesh is doing his PhD with me in the Safari research group, and this is one of his papers that he contributed to during his internship at the beginning of his PhD. Okay, Rakesh, please go ahead. Make sure you share the slides also.
Yeah. Yeah. This is okay? Okay.
We're seeing your presenter's view.
Can you start? Yes. Will we close the meeting? You should stop sharing this first.
Just
Or is hidden. Okay.
Yeah. Yeah, okay. Thank you so much. Thank you, Onur. So today I'll be presenting Flash Cosmos, which is in-flash bulk bitwise operations using inherent computation capability of NAND flash memory. And this was a recent work that got published in Micro 2022. And this was done in collaboration with Safari at ETH Zurich and Pohang University in Korea and the Research Institute at Montpellier and Kyungpook National University. So, okay. Okay, so let me jump to the executive summary. So bulk bitwise operations are widely used in many important data intensive applications, such as databases, graph processing, and cryptography. So the problem with performing bulk bitwise operations is that the performance and energy efficiency of bulk bitwise operations are bottlenecked by the data movement that is being done between the storage unit and the compute units, which is done through the memory hierarchy in the traditional systems and also in storage processing. In storage processing, the compute unit is closer to the storage, but yeah, it's still a bottleneck. And in some of the recent in-flash processing techniques, the serial data sensing is one of the key bottlenecks that is affecting the performance and energy efficiency of bulk bitwise operations. And also in prior in-flash processing techniques, these techniques provide very low reliability during computation because they can't leverage the ECC and data randomization techniques that typically NAND flash memory or the flash devices use. This is a bit of. So the goal of this work is to improve the performance and energy efficiency and reliability of bulk bitwise operations in flash processing. And to this end, we propose Flash Cosmos, which is flash computation with one-shot multi-operand sensing, an in-flash processing technique that is based on two key ideas. One is called multi-word line sensing, which enables multi-word line activation to perform these bulk bitwise operations with a single sensing operation, and also enhanced SLC mode programming, which increases the voltage margin between the erased and the programming states to provide higher reliability during in-flash computation. And to talk about key results, Flash Cosmos was evaluated with using 160 real 3D NAND flash chips and with the state-of-the-art SSD simulator on 3 real-world workloads. And this was done with the simulator. We evaluated the system-level performance of Flash Cosmos and some of the prior techniques. And the key results show that Flash Cosmos improves the performance and energy efficiency by 3.5 times and 3.3 times over state-of-the-art IFP technique while providing high reliability during computation. So the outline of my talk is to initially show what motivates us to do this work. And then we move to some background on NAND flash memory. And then we talk about, and we also derive some insights from how NAND flash memory is organized. And then we show our key technique, and then we talk about evaluation and summary. So let's jump to the motivation. So bulk bitwise operations are are prevalent in most of these application domains like databases, web search, genome analysis, graph processing, set operations, and hyperdimensional computing.
But as I mentioned, the data movement bottleneck between the compute units and the memory hierarchy significantly affects the performance of these bulk bitwise operations, because bulk bitwise operations themselves are very simple in nature, but they are performed on operands which could be in the order of gigabytes. So which requires the data to be moved to the compute units, and that creates a major bottleneck. So what is the data movement bottleneck that we are talking about? Let's look at a traditional system or a conventional system where we perform computation. And here we have a host processor, a main memory component, and a storage unit. So let's say the operands are being stored in the storage device. And we see that for performing these computations, we need to read the data from the storage device to the main memory. And the host processor reads from the main memory, and the computation is performed in the host processor. And we see that the typical bandwidth of a storage device, the external bandwidth of a storage device is around 8 gigabytes per second. This is considering a PCIe Gen 4 device with 4 lanes and 2 gigabytes per second of bandwidth for each lane. And we have the typical memory bandwidth of tens to hundreds of gigabytes per second. So to do that, to perform this computation, we need to move the data through the entire memory hierarchy, and then basically write the data back to the storage device. And here we see that compared to the main memory bandwidth, we see the storage bandwidth is very less, which will create the data movement bottleneck. So the external I/O bandwidth of the storage systems is the main bottleneck for data movement in outside storage processing or conventional systems. So to solve this, we need to move the computation closer to where the data resides. And to do that, we look at near data processing techniques. And here we see some prior works which have looked at near data processing, and we have works which have been done at different levels of memory hierarchy. We at SRAM cache level, we have compute cache, which is one of the main works. And at DRAM, we have Ambit, which was done at Safari. And then we also have Peanut 2 board for NVM-based main memory. And we also have for in-storage processing, we have a work called Biscuit. And for in-flash, we have a recent work called Parabit. And our focus is to look at these two areas, which is in storage and in flash, because we expect that large data sets do not fit into the main memory. So we look at works which are done at the storage level. So let's look at what in storage processing does. So in storage processing performs the computation using an in storage computation unit, which are typically embedded cores or FPGA. And ISP significantly reduces the data movement by transferring only the computation results to the host. So let's look at the same environment where we have a host processor, a main memory, and a storage unit. And inside the storage unit, you can see an in-storage computation unit and several NAND flash chips connected to the in-storage computation unit. And so massive amounts of data are read from the NAND flash chips to the in-storage computation unit where the computation is performed, and only the result is transferred to the host processor. So here the main challenge is that we have there is a storage internal bandwidth, which is the bandwidth of each channel which connects the NAND flash chips to the in-storage computation unit. And let's say here we have an example of 8 flash chips, which are 8 flash channels, which are connected to the in-storage computation unit, and each channel can support up to 1.2 gigabytes per second. And we see that the difference between the internal and the external I/O bandwidth is not so high. So here the main bottleneck becomes the internal I/O bandwidth of the storage device. So the storage internal I/O bandwidth is the main bottleneck in ISP. So the next logical step is to move the computation more closer to where the data resides. Now there is still a data movement that is happening to the between the flash chip and the computation unit within the SSD. Now we need to look at performing computation within the flash chip itself. So in flash processing, the computation happens within the flash chips, where the operands are being stored, and the computation happens when the operands are being read serially. So IFP fundamentally reduces the data movement bottleneck in storage by transferring only the computation results to the in-storage computation unit, which sends the data back to the host. So here we see the same figure. And as I mentioned, the computation happens on the flash chips, and then only the result is moved to the in-storage computation unit. This is a much better scenario compared to some of the prior scenarios that we saw, like ISP and the outside storage processing. And we only move the result back to the host. So this is reducing the data movement. But even here, we see a bottleneck, which is the data sensing. What do I mean by data sensing? So by data sensing, it means that the operands that are stored in the flash chips in different pages, they are being read serially. So they are read one after the other while the bitwise operation is performed. So let's look at what this data sensing bottleneck is. So in state-of-the-art IFP technique, which is parabit, they perform the bulk bitwise operations by controlling the latching circuits in the page buffer. Just a moment. Controlling the latching circuit of the page buffer. So here we have a storage device where we have an in-storage computation unit and number of flash chips connected to the to each channel. And if we see an individual flash chip here, we see a number of pages which are available and a page buffer. This page buffer is typically used for programming pages to the flash chips from the host or from the in-storage computation unit, or while reading, this page buffer is used to store the data. So let's say these bitwise operations or bulk bitwise operands are stored in each of these pages. Let's say we have many pages like that, like this, where the operands are stored. So in order to perform the bitwise operation, the current technique, what it does is it performs a data sensing, which is to read the operand. Then if we have to perform a bitwise operation, let's say a bitwise AND between two operands, then it has to read the second operand as well, and the result gets accumulated in the page buffer. So if we have to do it for 3 operands, then it has to be read again, and then the result gets accumulated in the page buffer again. So this cannot be done if there are thousands of operands. This creates a major bottleneck because each sensing operation is very expensive. So serial data sensing is a major bottleneck in flash processing techniques. This is one part of the one limitation of current techniques. There is also another limitation, which is the reliability issues that we see in the current techniques. So NAND flash memory suffers from high raw bit error rates due to many sources of disturbances. NAND flash memory can lose charge if it's not being programmed or erased frequently, which is called retention effect. Then we have another effect called read disturbance, where if the pages are being read frequently, then it increases the threshold voltage of the flash cell. And we also have a program interference, which is a disturbance caused during program operations. And these are typically the reliability of NAND flash cell is typically improved by using an ECC module or a data randomization technique but these in-flash processing techniques cannot use these ECC and data randomization techniques because the computation is performed within the flash cell and within the flash chips and during data sensing. So let's look at a diagram of a figure of a SSD device, and we see that the flash chips are connected to different channels, and they are connected to the channel processors, which is within the SSD controller. And we see that the ECC engine and the scrambler engine are present. Scrambler engine is present inside the channel processors, which means that if we have to correct these error bits, then the data has to move from the flash chip to the channel processors, which creates additional data movement bottleneck. So this is the reason why current in-flash processing techniques cannot use the ECC and scrambler engine to scramblers to correct the error bits. So let's look at an example of how these error bits are being persisted in current in-flash processing techniques. So if let's say there are, sorry for that. So if there are some error bits in each of these operands, when we do the in-flash processing or in-flash bulk bitwise operation, when the data sensing happens, these error bits are being persisted, and when we perform a bitwise operation with many operands, then it can the number of error bits can also get compounded. So this is one of the key limitations of prior in-flash processing techniques. So prior IFP techniques, if they can't correct the error bits, then it requires the applications to be highly error tolerant. So the applications have to tolerate such errors, and then it can perform these bulk bitwise operations within the flash memory. So our goal is to actually address the bottleneck of state-of-the-art IFP techniques, which is to reduce the serial sensing of operands and also make the in-flash processing more reliable. So this is our proposal. So we enable computation on multiple operands using a single sensing operation and provide high reliability during in-flash computation. So what we intend to do is we actually want to read all the operands in a single shot, and the result should be accumulated in the page buffer, unlike the previous technique. So let's look at some background and derive some insights into how current NAND flash memory organization can perform this simultaneous data sensing. So a NAND flash cell can store data by adjusting the amount of charge in the cell. So let's say if a flash cell is erased and it has no charge or low charge level, then it means that it's storing a bit 1. And if it is programmed and has high charge level, then it stores 0. And when this flash cell is activated, if it is in the erase state, then it acts as a resistor. And if it is in the program state, then it acts as an open switch. So a bunch of these flash cells, when it's connected in series to a bit line, it forms a NAND string. And you can see that there are different cells storing different values, which means that some of them are erased, some of them are programmed. And if, let's say, we want to read only the first cell in the NAND string, then these are some of the non-target cells that we don't want to read. And these, by passing a high pass-through voltage through these cells, these actually act as resistors, irrespective of what is the data stored in them. So this is the target cell that we want to read, and because it has a value 1 or it is not programmed, it acts as a resistor. So when we send during a read operation, when the bit line current flows through to the NAND string, when it acts as a resistor, it can the current can flow through the NAND string, and the sensing circuit at the end of the bit line would read it as a 1. So let's say the same cell is programmed and we want to read that cell. So in that case, when we perform a read operation, it acts as when it's activated, it behaves like an open switch, and the current cannot flow through the NAND string because it's an open switch, and then it is read as a 0 by the sensing circuit. By activation, I mean that we need to we need to provide a reference voltage to these cells during the read operation. So let's look at the organization of a NAND flash block. Here we see that in a NAND flash block, we have a bunch of bit lines, and a NAND string is connected to each bit line. And these flash cells are connected in the horizontal direction, and that is called a word line. And word line is what is typical forms a NAND page, which is where the data is stored. And these cells connected horizontally is a word line. So a single word line controls a large number of flash cells, and this provides high bit level parallelism. So that was the organization of a single block. Now we have multiple blocks, and the key insight is that these bit lines are shared across these different multiple blocks, and each of these blocks will have different NAND strings connected to the bit line. So one of the insights that we derive is that looking at this kind of organization, if we look at the NAND string within a single block, we see there is a similarity between the NAND string in the single block to what is there in the digital AND circuit, where the transistors are connected in serial. And when we look at multiple blocks or different blocks, we see a similarity with digital OR circuit, where the transistors or the cells are connected in parallel. So this gives us some insight into how we can perform a bitwise operation across multiple operands. So in Flash Cosmos, we enable in-flash bulk bitwise operations on multiple operands with a single sensing operation. And that is what we wanted to achieve. And we have two kinds of multi-word line. So to do that, we introduced multi-word line sensing operation, which is one part of it is to perform bitwise AND operation, which is to perform bitwise AND within a block. And so to do that, we have an intra-block MWS operation, which is, as I said, within a block, and it simultaneously activates multiple word lines in the same block. So here we take an example of 4 word lines which are connected, which are there in a block, and we want to read only 2 word lines within that block. So we simultaneously activate 2 word lines, and so depending on the charge level in the cell, it either acts as a resistor or as an open switch. So when we read these 2 word lines, so what happens is when the bit line current passes through the NAND string, depending on whether the cell acts as a resistor or as an open switch, the current passes through the NAND string, and the sensing circuit at the end of the bit line reads the value. So when we see that if there is an open switch in the NAND string, then the current doesn't pass, and it acts as the result would be a 0. So if all of the cells in the NAND string have act as a resistor, then we see that the result would be a 1. So only when all the target cells are resistors or act as store 1, then we get a result of 1, which is what is a typical AND operation. So let's look at a scenario where we have to read 4 word lines. And similarly, here we see that the bit line passes through the NAND string. And even if there is a single open switch, then the current doesn't flow through the NAND string, and the result would be a 0. So this is the result that we expect from a bitwise AND operation. So the intra-block MWS operation enables bitwise AND of multiple pages in the same block via a single sensing operation. So there is another MWS operation which is called inter-block MWS, which performs simultaneous activation of multiple word lines across different blocks. And this performs bitwise OR operation of the stored data in word lines across different blocks. So when we want to read, when we simultaneously activate 2 word lines from different blocks, even if there is, even if it's an open switch or a resistor, if there is only a single resistor in the, if the cell acts as a resistor in one of the blocks, it's still, the result would be sensed as a 1, because the sensing circuit will get the bit line current, or will sense the bit line current flowing through the NAND stream, because it's connected in parallel. So, so a bit line reads as a 0 when all the target cells store 0. So when we want a 0 here, we want all the cells acting as open switches. So this is a case with 3 blocks, and we see the same behavior here as well when we activate 3 word lines from different blocks. So even if there is one target cell which is acting as a resistor, then we see the result as 1. So interblock MWS enables bitwise OR of multiple pages in different blocks using a single sensing operation. Now we have looked at bitwise AND and bitwise OR. Now we can also support other bitwise operations in Flash Cosmos, and to support bitwise NOT, we can actually exploit the inverse read operation, which is already supported in modern NAND flash memory for copy back operations. And to perform bitwise NAND and OR, we can actually perform bitwise AND and OR operation and enable the inverse read operation to get the inverse of that. So that will give us bitwise NAND and OR. And we can also perform bitwise XOR and XNOR, because by so this feature is also supported by NAND flash memory, because it can enable, it can perform XOR between the latches which are provided for performing a triple level cell program or multi-level cell program. So this was what we just saw was to perform bulk bitwise operations on multiple operands with a single sensing operation. Now we also look at how we can increase the reliability of the in-flash bulk bitwise operations. And we do that using enhanced SLC mode programming. So SLC mode programming, which is single level cell mode programming. In a single level cell, we store only 1 bit per cell. It can be a 0 or a 1. So this actually provides a large voltage margin between the erased and the programmed states. So you can see that there is a large voltage margin between the 2 states compared to an MLC, which I'm not showing here. We, based from our real device characterization, which is there in the paper, which I encourage you all to go through it. We see that it's still very high. This voltage margin is not sufficient to mitigate the disturbances that we see in the NAND flash memory without the use of ECC and data randomization. So SLC mode programming is still very highly error prone without the use of ECC and data randomization. So what we want to do is to increase the voltage margin between the 2 states. And to do that, we use something called enhanced SLC mode programming, which further increases the voltage margin between the 2 states. And we see that the end result of ESP is shown in the green, and it's much it's beyond the original SLC mode programming. So by increasing the voltage margin, we mitigate the disturbances which cause the cells to lose charge or the cells in the array state to gain some charge and move to the right. So ESP and how we do that is to add additional steps to the SLC programming sequence, which is done using a technique called incremental step pulse programming. And by adding more steps, it actually increases the latency of the program operation, but we also achieve high reliability. So ESP improves the reliability without the use of ECC or data randomization techniques. And ESP can improve the reliability of prior in-flash processing techniques as well, if they want to adopt this this technique. So, so now we have looked at how we can support different bitwise operations and how we can do it at very high reliability. Now we need to do this, we need to support some new flash commands that the SSD controller should support. And to do that, we support one command called MWS, which performs an intra-block or an inter-block MWS, and it also supports inverse read and accumulates the results of all the read operations or the sensing that we do for the bulk bitwise operations. And to do that, we introduce an ISCM command slot within the for MWS operation, and this allows the flash controller to turn on 4 different features, such as inverse read mode that I mentioned. And also, because unlike a regular read operation, we support where only one page is being read at a time, because now we have to read multiple pages or multiple word lines, we need to provide a page bitmap to specify the different word lines that needs to be activated for MWS operations. And that is provided as part of the address slot. And we also have 4 address slots for the interblock MWS command, which you can see here, separated by a continuous slot. So you have 2 address slots here. So if you provide 4 address slots, then you can actually perform a combination of inter and intra-block MWS operations. So you can realize 4, let's say 4 AND operations and 4 OR operations simultaneously. So ESP command is a new command that we support, which acts like a regular program command in NAND flash memory, but it actually increases the voltage margin between the 2 states. And we also have XOR command, which performs the XOR between the different latches in the NAND flash chip. So let's look at an operational example of how to perform bulk bitwise operations. So we have this equation which we want to realize, where we perform a combination of bitwise OR and bitwise AND, and the operands are being stored in 4 different blocks here, A, B, C, and D. And we to do this, we actually break the equation into 2 parts. One is the second part of we first look at the second part of the equation, and then we come to the first part. So for the second part, we have 2 bitwise OR operations and 1 bitwise AND operation to perform. So, but because of the power consumption of bitwise OR operation, the high power consumption of bitwise OR, because we are activating word lines across different blocks, what we do is we use De Morgan's law to try to use as many bitwise AND operations as possible. And to do that, we actually store the inverse data of the operands in the block 3 and block 4 to perform bitwise AND of the inverse data to get the bitwise OR operation. And we perform a bitwise OR between the 2. So you can see that so we specify the first operand and the different word lines to be stored within this page bitmap, and we also store the operands D2 and D4 using the page bitmap here, and we do that in different address slots. So this will actually perform we'll realize the second part of the equation. So we issue one MWS command to achieve the second part of the equation by enabling the inverse read mode, because we are storing inverse data, and we initialize the different latches, because this is the first operation that is being performed of the bigger equation. And now once that is done, we come to the first part of the equation, where we have bitwise AND of 4 different operands along with the bitwise OR. So to do that, we again send 2 different commands. We send we issue one command, MWS command, but with 2 address slots, which is where we specify A1 using this, and the B operands are being specified in the second slot. And this, while doing this, we disable the inverse read mode, because these operands are the bitwise operation is performed on the actual operand data and not on the inverse data. And also we disable the initialization of the latches, because we want the result to be accumulated with the first phase of the operation, or the previous MWS operation. So once we do that, the result gets accumulated in the sensing and the cache latch, which is present in each NAND flash chip. So that kind of gives us an idea of what Flash Cosmos is, and what are the different operations supported in Flash Cosmos. Now we look at evaluation. So in evaluation, we have 2 kinds of evaluation. One is where we evaluate the feasibility and reliability of Flash Cosmos in 160 real state-of-the-art 3D NAND flash chips. So in our real device characterization, we validate the feasibility, performance, and reliability of Flash Cosmos. And we also, as I said, we use 160 48-layer 3D TLC NAND flash chips. 48-layer means that in each block we have 48 word lines. And we have tested around 3,600,000 word lines. And these word lines were tested under worst case operating conditions, which is 1 year data retention time at 10,000 P cycles, and the worst case data patterns, which is where we use a checker data pattern to store data in the word lines, which causes the worst case disturbances that we can get. So the results of the real device characterization shows that both intra-block and inter-block MWS operations require no changes to the cell array of commodity NAND flash chips. And we can activate up to 48 word lines for intra-block MWS operation, and up to 4 word lines at the same time for inter-block operation, MWS operation. And this comes at a small increase in the sensing latency of up to 10%. So compared to a regular read operation, the sensing latency to perform multi-word line activation is only just 10% of the latency. And it also, ESP helps in significantly improving the reliability of computation results, and we achieve 0-bit errors in the tested flash cells. Now we look at a system level evaluation where we use a state-of-the-art SSD simulator, and we use 3 real-world applications to perform bulk bitwise operations. So we use MQSIM, which is a state-of-the-art SSD simulator, to model the performance of Flash Cosmos and some of the prior techniques. And we use 3 workloads where in each workload it performs bitwise operations of a number of operands. We choose bitmap indices, which is a database workload which performs bitwise AND of up to 1,000 operands. Then we have image segmentation, which performs bitwise AND of only 3 operands, but these 3 operands are very large in size. And then we have K-clique star listing, which is a graph processing workload which performs bitwise OR up to 32 operands. And the baselines that we model here are outside storage processing, which is where the computation happens in the host CPU. And to do that, we model a multi-core CPU for this. And for in-storage processing, where the computation happens within the storage, but in the in-storage computation unit, we model an in-storage hardware accelerator. And the state-of-the-art IFP technique, which is parabit, is also modeled for this. So we look at the results for this. On the left side, we see the result for the overall speed up, and this is normalized to the outside storage processing. And on the right side, we see the energy benefit that we get from Flash Cosmos. And the Flash Cosmos actually improves the performance by up to 3.5 times over Parabit, which is the state of the art, and also over 25 times over ISP. And the energy efficiency that we get is up to 3.3 times over Parabit and 13.4 times over ISP. And we see that from our evaluation, we see that if the number of operands increase in the workload, then the benefits that we get, energy and the performance benefits that we get from Flash Cosmos is only increasing. So this is the link to our paper, and I would encourage everyone to go through the paper and yeah. So in summary, Flash Cosmos is the first work to enable multi-operand bulk bitwise operations with a single sensing operation and provides high reliability. And it significantly improves performance compared to the prior techniques, and also provides high energy efficiency. And it comes at a low cost without requiring any changes to the commodity NAND flash array. So that's the end of my talk. I'll be happy to take questions. And thanks for listening.
Any questions for Rakesh? I don't see the room, but yeah, maybe I'll make some comments. So as we have seen in class, we've talked about Ambit. You can put me on the screen also if you can. You talked about Ambit, and this is an example where you can do something like Ambit on Flash. In fact, it's much more powerful than Ambit, as you can see. So it's actually good to enable such operations in other memories. So people have shown that you can do this in other non-volatile memories, but this paper shows is the first one to show that you can do it on Flash on many operands at the same time on real Flash chips, right, Rakesh?
Yes, yes or no?
Yeah, and also it tackles reliability in a way that no other prior work tackles, in the sense that it actually tries to make this completely reliable by proposing techniques to avoid errors due to computation. I mean, there's analysis in Ambit certainly for reliability, but this is performed on real Flash chips using real Flash incremental step pulse programming methods. So it's important to consider reliability more going into the future, since analog computation can have a lot of noise issues, as we have discussed in class. So there's a lot more future work that can come in this area. Okay, I think last chance for questions in the room. Otherwise, we should take a 5-minute break before we start the next talk. We're running a bit late, but I think it's good to take a short break to relax, and then people can come back and maybe they'll ask more questions for the next talks.
I have do you see the possibility of generating true random numbers in SSDs?
Yeah, I mean, that's something which we need to investigate. That's a research direction that's very interesting. We see some recent works which look at physical unclonable functions, which is also very critical for cryptography. So this is something which is possible in NAND flash memory and needs investigation. Yeah.
Yeah, so there has been work in that area, actually. There are works from 2010s that look at random telegraph noise in flash memory. and they actually exploit the random telegraph noise to generate random numbers. Yeah, maybe we'll put it on the chat or somewhere. But yes, as we discussed in this class many times, all memories are in a sense similar. You just need to find ways to exploit a specific memory technology to achieve your goal, whether it's true random numbers, physical unclonable functions, bitwise operations. So understanding the memory type to enable operations is the creativity, let's say, and the challenge to make memory do some computation for you, let's say. Okay, I think we should take a break right now so that we don't go late. So if I guess you can start 5 minutes later. It'd be good to set up in the meantime for the next talk, which will be Nika.
Okay.
Do you hear me on Zoom? Do you see everything properly?
Yes, we can hear you, and also you see everything properly.
Okay, let's get. Can you hear me?
Okay, good.
Okay, let's get
Yes, I
started.
can hear you.
Yeah, we shouldn't waste much time because we have 2 papers and not enough time. Hopefully you'll get us back on the better curve in terms of timing. Okay, so Nika is also a PhD student in my group, and this is her first, let's say, publication in her PhD on GenStore. She's going to talk about in-storage genome filtering, and this was published in ASPLOS. So Nika, please go ahead.
Okay, cool. Thanks, Onur, for the introduction. And hi, everyone. Today, we will talk about GenStore, a high-performance in-storage processing system for genome sequence analysis. So genome sequence analysis is critical for many applications, such as personalized medicine, outbreak tracing, and evolutionary studies. And over the past few years, also, we've seen the increasing importance of it in medicine. So genome sequencing machines extract the smaller fragments of the original DNA sequence known as reads. So when we have a sample collected from a patient or some organism and we want to analyze it, the sequencing machines usually cannot read the whole thing at once. So they generate these smaller fragments. So we call them reads. So read mapping is the first key step in genome sequencing analysis that aligns reads to some potential matching locations in the reference genome. So imagine we have a patient that we want to conduct some personalized medicine task for them. And then we have a reference genome of humans. So we want to align these reads to these reference genome and see where they match. And also for each of these matching locations, the alignment step finds the degree of similarity between these sequences. So based on these differences, then we can make some medical or biological conclusions and then move to the next step. So these are basically very important. But calculating the alignment score requires computationally expensive approximate string matching to account for differences between the reads and the reference genome. And these differences can occur due to different reasons. For example, the sequencing machine can have some error or the genetic variation. And then we want to understand these variations so that we can understand the genomic or like the medical concept that we're analyzing. So read mapping performs alignment, that computational expensive step, on large genomic data sets containing millions of reads. So you would usually collect like many reads from the sample, and then you need to perform that operation on them. So therefore, read mapping is both computationally expensive and also incurs high data movement overhead from storage up to the computation units. So over the past few years, due to importance of this application in healthcare and also in genomics, so there's been significant effort into improving read mapping performance through their efficient heuristics, accelerators, or devising some filters that would prune some of these reads that wouldn't align any random reference genome. And they've targeted different parts of the system stack to implement these optimizations. While these optimizations address the computation overhead or also data movement overhead from main memory or cache hierarchy, none of them addresses data movement overhead from storage, whose impact actually becomes larger when the other overheads gets alleviated. So in this work, our key idea is to filter reads that do not require a computationally expensive step of alignment inside the storage system, so that we can fundamentally address the data movement right from where the data is originally stored. Examples of the reads that would not require that computationally expensive step would be exactly matching reads, basically the reads that would match exactly some places in the reference genome and do not need the approximate string matching, and also non-matching reads. that do not have any potential matching location in the reference genome, and then altogether can skip performing the approximate string matching. Going through the talk, I will explain with some biological examples why these things would happen frequently, actually. So with all these benefits, implementing it actually inside the SSD is challenging, because read mapping workloads can exhibit different behaviors. So the reads that we want to filter out would be different across the use cases based on the genomic content of the reads sequences that we collect. And we have limited hardware resources inside the storage system. And in this work, by addressing these challenges, we propose GenStore, which is the first storage processing system designed for genome sequence analysis, and that addresses both the computation overhead and data movement overhead from storage. And it provides high performance and energy benefits compared to state-of-the-art software or hardware read mappers. So that was the overview of my talk. Now I will go through some background of read mapping so we understand it a little bit more detail for the sake of this talk, so we can understand the design better. So mapping reads to reference genome, as we discussed, requires computationally expensive operations on large data sets. And so the search space in reference genome is actually really large. For example, for a human reference genome, we have like more than 3 billion characters. So we want to see for each read, what is a potential location for it and what are the exact differences. So usually, in order to mitigate these costs, read mappers, state-of-the-art read mappers involve several heuristics. So we can, in high level, abstract them in 3 key steps. So let's go through these steps. So first of all, in order to enable a more efficient search in this large reference genome, we utilize an index. So this index structure contains k-mers. So k-mer is a subsequence of length k. Here, for example, we're showing a 3-mer in the index, several 3-mers. So it has different k-mers and that are extracted from the reference genome, and the location of these k-mers in the reference genome. So now, given this index structure, I will walk through these 3 key steps of read mapping in high level. So the first one is seeding. We want to find some potential matching locations or seeds in the reference genome, because we can't go through all the reference genome to find differences of reads across like every single location, right? So we want to find some candidate locations. How do we do that? For each read, we again extract k-mers. Here I'm extracting 3-mers. And look up these k-mers inside the index. And for the k-mers that would hit in this index, we mark their location in the reference genome as seeds or potential matching locations. So okay, so far so good. We know that we don't need to search all the reference genome. And then after that, we do some seed filtering or chaining. Still, we want to see if we can filter out some of these potential locations. So we end up performing that computationally expensive alignment on a fewer number of locations. So using less computationally expensive approximation of alignment score, we would basically filter these. So this step would be much less computationally expensive than the actual alignment, and uses some chaining score to filter these some of these locations. So we refer to this step as seed filtering or chaining. And if a read has no potential matching location left at the end, it just gets discarded. So we know that it would not align anywhere. And for the remaining reads, we go to the third step, which is the computationally expensive alignment, to determine the exact differences between the read and the reference genome, using that approximate string matching that we talked about. Okay, so that is a high level, let's say, functional overview of this. Given that, now after this, we go to the motivation part. So we want to analyze what are the potential benefits of in-storage processing. And to do that, we experimentally demonstrate some case studies on real-world genomic read data sets. So we consider various read mapping systems, either software or hardware, basically for each of them state-of-the-art samples and various state-of-the-art SSD configurations. And we analyze how will be the benefit of storage processing ideally in these. And we make several observations. I will summarize these observations for you. First is that the ideal in storage filtering significantly improves performance by reducing the computation overhead and data movement overhead right from the storage. So you don't need to carry the data that you would eventually discard. You wouldn't need to carry it to main memory, to caches, to processing units. And filtering outside SSD provides relatively lower benefits because it does not reduce data movement overhead from storage. And also it needs to compete with read mapping for system resources. For example, for IO external bandwidth or for main memory bandwidth. So it needs to compete with the read mapping also. And we also observed that a hardware accelerator that reduces the computation bottleneck makes IO even a larger bottleneck in the system. And that is an important point because over the past few years, we've seen, as I mentioned, a lot of efforts put into improving these read mapping performance. And now it shows that the KIO is emerging as going forward into a more important issue that needs to be addressed. So motivated by these observations, our goal is to design and storage filter for genome sequence analysis in a cost-effective manner. And we have three key design objectives in our new system. First is that the filter needs to provide high in storage filtering performance so that when we're doing in storage filtering inside the SSD, we can overlap the time it's spent on this filtering with the read mapping of remaining reads happening somewhere else. And second, it should be applicable to various genomic data sets. So it should support reads with different properties and different degrees of genetic variation in the compared genomic sequences. And of course, it should incur low hardware costs. And to this end, we propose GenStore, which is the first first in storage processing system for genome sequence analysis. And our key idea is to filter reads that do not require alignment inside the storage system and send the reads that do not get filtered to and need substantial processing to the host system for further analysis. And that can be anything, right? That can be like a normal CPU or a GPU, I don't know, like an accelerator. So it can just be integrated with various read mapping systems and augment their benefits. And so as we discussed, there are two challenges. So different behavior across read mapping workloads and limited hardware resources in the SSD. We will dive into these in more detail. So by different behavior across reads, so let's take a look at different read types and some filtering opportunities based on that. So sequencing machines produce one of two kinds of reads. So either short reads that are highly accurate and short, and long reads that are less accurate and long. And there's been also efforts into improving the accuracy of these long reads. I can maybe point out to that in the end as some of expansions or like areas, directions GenStore can also move to. So reads that do not require expensive alignment step, I try to explain based on these, let's say, high-level classification of read types. So exactly matching reads, basically reads that do not need approximate string matching during alignment, would be reads that have low sequencing error rates, which would be short reads, and low degree of genetic variation. So let me give you an example. For example, humans are genetically very similar. And on average, 80% of the reads would map exactly to a human reference genome. So, and the non-matching reads, which are reads that do not have any potential matching location in the reference genome. So examples of them would be some reads that have a lot of high degree of sequencing error rates and high genetic variation. And a common example of high genetic variation, we can think of virus, right, and bacteria, because these things evolve very fast. So usually they have a lot higher genetic variation compared to, I don't know, humans. And also there are like various other use cases. We talk about it in the paper. If you're interested, please check. Okay, so what we do is that we do a thorough analysis of read mapping process for reads with different properties, different degrees of genetic variation across different species. And according to the opportunities existing there, we designed 2 low-cost storage filters, GenStore EM for exactly matching reads and GenStore NM for non-matching reads. So let's take a closer look at GenStore EM. GenStore EM accelerates read mapping by using an efficient in-storage filter to filter reads that have at least one exactly matching location in the reference genome, using simple operations without requiring alignment. But the key challenge is here large number of random accesses per read to the reference genome and its index. So if you remember, we have this index, and for each read, we have several k-mers, and then we need to look randomly different places of this index, and then later on go check the reference genome at random places. And actually having these random accesses to large data structures is very challenging inside the SSD because random accesses to flash chips are expensive, and we have limited DRAM capacity inside the SSD. So usually each SSD typically has like 1 gigabyte of DRAM for every terabyte of storage capacity. So that is a challenge that we aim to solve. So let me talk about two ideas in designing the data structures. So first, we introduced a read-sized k-mer to reduce the number of accesses per each read. So if you remember, we have this read and then several k-mers extracted from it. So we have to have several accesses per each read for these k-mers extracted. So what we do is that we consider a read to be a k-mer. So at least here, we have 1 access per read. So we reduce the number of accesses like that. Then, since now we have 1 access per read, then we can sort these things, because when we sort these read-sized k-mers, we can avoid random accesses to the index if both of them are sorted. Why couldn't we sort before? Because when we had several k-mers, we had to go here and there random places, so we could not know how to sort, right? But here it's like 1 access, so that gets enabled by it. So we can have sequential scan of the read set and the index that are located in the NAND flash chips. So let me show you this key idea of GenStore EM with a simplified example in which each read is consisting of 10 characters. Usually the short read would take like few hundred characters, let's say 150. But here I am just showing 10 for the sake of example simplicity. So we have 2 data structures. One is a sorted read table that each entry of which stores a read and a unique ID of this read. And then we have sorted k-mer index. So each entry of it contains a unique read-sized k-mer extracted from the reference genome. So if you look at the earlier example that we had 3 mers, here we have 10 mers. So because that's the size of the read. And also location of these k-mers inside the reference genome. So it's very similar to the previous index we talked about. It's just that each k-mer is larger. And both data structures here are sorted by read and k-mer in alphabetical order. So we sequentially scan through these data structures in 3 different ways based on the comparison result of the current read and the k-mer. So let me go through these 3 ways. So imagine we are now at the top of this table and we want to compare these things. Okay, we compare, these things are equal, exact match, good, we're happy about it. We filter the read and we go next. Okay, now we see that this thing, the read is bigger than the k-mer, So what does that mean? So we've been sequentially scanning, right? So if that k-mer would have matched anything, we would have already encountered it. So when the k-mer is smaller, it means that, okay, it's not going to match anywhere. So let's go to the next one. Okay, we went, good. So now we're the next one, and we see that the k-mer is now bigger than the read. So again, we understand that the read wouldn't match anywhere in the k-mer because we've been sequentially scanning, we would have seen it otherwise so far already. So, okay, when the read doesn't match, we understand it's not an exact match. So it needs to go to the mapper. To the read mapper wherever outside the storage it is located. And then we go to the next element. So using these data structures and this like sequential scanning of them, we avoid random accesses. And we only need some simple low-cost logic, that comparator that I showed. So despite the key benefits that I talked about so far, this read-sized k-mer index takes up a large amount of space. So for example, for a human index, it will be 126 gigabytes. Why is that? Because we have larger number of unique k-mers. So let's say 10-mer, unique 10-mers are like larger counts of them than unique 3-mers. That's one thing. And also the each k-mer stored, it's taking a larger space. So we further reduce the overhead of GenStore EM by replacing the read-sized k-mers with a strong hash value of each read that acts as both sorting criterion and fingerprint of each entry. And using this strong hash values of these read-sized k-mers, we can reduce the index size by 3.9 times. But this index is still larger than the baseline index that we saw in like the background slide, but that is fine because we have, let's say, large capacity inside the SSD, and also we can stream through it with high bandwidth inside the SSD because we can distribute it across the channels and read through them concurrently, so we have the high bandwidth. So that shows actually example of like hardware software co-design performed here specific to the underlying hardware, because the solution basically is tailored towards like in-storage processing paradigm. Okay, so now let me show you the overall operation flow of GenStore EM with the sorted read table and sorted k-mer index that we talked about in the NAND flash memory. So that is distributed across different channels and dies and planes. So we can access them in high bandwidth since they're evenly distributed. So we can leverage the full internal bandwidth of the SSD. And we have that simple comparator logic in the SSD controller. So GenStore EM then has two steps. First is that we sequentially read the two tables from the flash chips to the SSD's internal DRAM. In a batched manner. Since we're reading them sequentially, we don't need to bring the whole thing in the DRAM, right? So we bring like a few hundred megabytes each time in batches. So, and the next step is performing exact batch filtering within each read batch, just using the simple comparator operation. And step 1 and 2 can be performed in a pipelined manner, right? You can bring one batch, and then meanwhile, do exact match filtering on a previous batch. And then that happens in pipeline. And then meanwhile, you can send the reads that you know they're not going to be filtered to the host system. And then that means that while you're doing the filtering inside the SSD, the unfiltered reads can already be concurrently processed by the host system. So which actually allows GenStore to hide that time of filtering and also be integrated with different type of read mappers. So now let's take a closer look at GenStore NM. If you remember, we talked about these 3 key steps, right? Seeding, seed filtering, and alignment. So the seed filtering or chaining. Basically using chaining, GenStore NM filters most of the non-matching reads that would not align to any subsequences in the reference genome. And recall that the chaining filter calculates a similarity score of each read called chaining score and filters the reads that actually at the end of this step have no potential matching locations left. But then calculating this chaining score inside the SSD can be challenging because finding the best chaining score requires performing many iterations of a dynamic programming algorithm for all seeds within a read. And that can actually be costly because we need to perform it on many seeds for reads, particularly long reads that have many seeds, like up to millions. So that would require a lot of buffer space inside the SSD, and also in order to keep up with the throughput that we want to have, we need to have basically a lot of, let's say, concurrent hardware resources. So that would incur a lot of area cost. So to reduce the cost of chaining, GenStore and M uses a lightweight chaining filter. So what we do is that we selectively perform chaining on reads that have a small number of seeds. So what were seeds? Seeds were potential matching locations based on the K-mer lookups that we did, right? So if a read has few seeds, then we selectively perform this chaining inside the SSD on that. And otherwise, if the read has a lot of seeds, a lot of potential matching locations, we would just send it to the host system to perform the complex chaining. So that is based on our observation on various real genomic data sets across different species. Let me show you an example here. So what does this plot show? On the y-axis, we see the alignment probability, and then the x-axis, we see the number of seeds per read. So this plot goes on, like I've truncated it to show this part of it here. Basically goes on the x-axis. So what we see here is that if a read has a large number of seeds, it will with high probability align somewhere in the reference genome. So it's fine if we don't filter it inside the SSD, because most likely it won't be filtered anyways. So that's one thing. And the second thing is that we observe across various use cases that a lot of reads actually would fit within like this first part with like lower number of seeds. So you can have a lightweight chaining filter inside the SSD to only work on that specific part without basically losing so much filtering opportunities as I discussed. So again, reads with a sufficiently large number of seeds are very likely to align to the reference genome, and filters. So by doing the selective chaining, we filter many of non-aligning reads without costly hardware. And for the detailed design of this GenStore and M, please refer to our paper. You can take a look at various analysis we do in real data to show this trend, and also the exact hardware design of it inside the SSD. So now I will go into our results. We evaluate the following systems. So BASE, which is the state-of-the-art software or hardware read mapper for both short and long reads, and GS, which is BASE integrated with GenStore. So that shows that regardless of the type of the read mapper you have, you can integrate GenStore with it to further improve performance of the system by filtering unnecessary data. And then we also evaluate these mappers and systems with various SSD configurations, a low end, medium end, and a high end SSD. And for details about our methodology, please refer to the paper. So we analyzed the benefits of GenStore EM for a 22 gigabyte short read set where 80% of the reads exactly match some subsequences in a reference genome and can be filtered. We show the benefits of it on hardware and software mappers. We show up to 2.5 times speed up compared to the software baseline and 3.3 times speed up compared to the hardware baseline, and an average 3.92 times energy reduction. So we analyzed the benefits of GenStore and M for a 12 gigabyte long read set with very high degree of genetic variation compared to the reference genome, where more than 99% of the reads are being filtered. So we also analyzed, this results for different type, like different percentage of reads being filtered in the paper that you can check. So we show up to 27.9 times the speed up, 27.9 times speed up compared to software baseline, and 19.2 times speed up compared to the hardware baseline, and an average 27.2 times energy reduction. So we find area and power values of GenStore by synthesizing GenStore EM and NM using a 65 nanometer technology node, and find that for an 8-channel SSD, the area of GenStore here is 0.2 millimeters square, and power is 26.6 milliwatts. Then we scale the area to lower technology nodes, and find out that compared to like a 14 nanometer Intel processor, GenStore's area consumption is only like 0.006% of that processor's area, and less than 9.5% of the 3-arm processors in a SATA SSD controller. So actually, this is a older SSD controller that shows that even on this, like, let's say a low-end SSD controller, the area consumption is low. And for the more advanced controllers that have more hardware components in the controller, the relative area consumption would be even lower. So now let me talk briefly about other results that we include in the paper. So if you're interested, you can take a look. We try to show effective read set features on performance. And for that, we scale the data size up to 440 gigabytes. And filter ratio, basically, what will happen if, I don't know, we have different use cases in which different fractions of the reads would be filtered. And performance benefit of an implementation of GenStore outside the SSD, because so as you see, we've done some hardware software co-design, and we wanted to see these optimizations, the benefits they would provide outside the SSD. In some cases, it provides performance benefits due to more efficient streaming accesses, but on average, it provides significantly lower benefit compared to GenStore's implementation inside the SSD. And we also show more detailed characterization of null-matching reads across different read mapping use cases and species. So we can get an insight into where, like in which read mapping use cases, these filters would be actually useful. And we have also a discussion on that in the paper, talking about how in the future GenStore's applicability would evolve. So now let me conclude by giving a summary of what we discussed. So there's been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters. And while these approaches address the computation overhead, none of them alleviate the data movement overhead from storage, whose impact becomes even larger as other overheads get addressed. And our goal in this work was to improve performance of genome sequence analysis by efficiently and effectively reducing unnecessary data movement right from the beginning, from storage system. And we don't move the whole data to the rest of the system. And our idea was to filter reads that do not require the expensive alignment computation in the storage system to fundamentally reduce data movement overhead. And the challenges that we had to overcome was read mapping workloads can exhibit different behavior across different use cases based on the genetic content of the read set or the type of analysis we want to do, and there are limited available hardware resources in the storage system. And then by addressing these, we proposed GenStore, which is the first storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. And we show that it provides a significant performance and energy benefits compared to state-of-the-art hardware and software mappers. Basically, it augments those to provide even like further performance improvement. And GenStore is open source. You can take a look at our repo in Safari GitHub. We try to basically have a walkthrough into how the software analysis is done, or like the hardware analysis. And if you're not also familiar with how this genomic pipeline would work, or not confident with the idea, you can also take a look. You can see how to download the data, how to kind of like run it and analyze it and understand it. So we try to put scripts there too, so you can play around and can like make some observations if you're interested. Yeah, so that was the summary of not summary, but that was the presentation of this project. Yeah. So let me know if you have any questions. Thank you.
First of all, it's a really nice work. I really like it.
Thank you.
And second is like for short reads, for example, I think like 80% of them you can match inside of SSD.
It depends on the species, right?
Yeah.
So for humans, that's on average the case.
Yeah. And then in case for humans, right, like then 15% is to send out of the SSD.
Mm-hmm.
Out of 15% you still send it out.
80 is 20, right? 100 minus 80 would be 20.
Okay, so 20% is to send it out of the SSD.
Yes.
So basically, like out of this 15% then probably they match with one edit distance. And then in the other,
I got your point. It's like, oh, okay. Mm-hmm.
Yeah, in the other version for long reads, what you do, you have a like lightweight chaining.
Mm-hmm.
So why don't you apply this lightweight chaining for one distance in these 50% so that 50% still be performed inside of SSD and 5% only go out?
So no. So that 15% wouldn't be like they wouldn't align. So based on, I don't think that is the case. They would actually align. I don't think that among that. So, but regardless of the exact number, let me focus on a question from perspective of combining the filters. Yeah, I definitely agree. The filters can be combined. So if you have a data set that we know part of the reads would exactly match and the other ones would not, then you can run both sets of filters and even filter more data. So that is correct. But it's also important to know that for long reads, the exact matching does not occur. So you cannot combine them for long reads. You should use GenStore NM. But for short reads, yes, you can use both for sure.
Second question is like the prior work, like flash commons. It shows like you can leverage like the internal peripheral of the flash itself to perform computations because they wanted to fight the movement of data between the flash and the DRAM inside of SSD, like fighting the in storage data movement. You see like the operators that they show here, we can use them to build filters that we can perform this analysis inside of the flash itself.
Yes. So this basically, what GenStore here enables is that it would turn the otherwise random accesses into sequential accesses, let's say for this, one of the use cases that we saw. So for that, now that we have these sequential accesses, yes, we can understand if we can use processing using flash to further improve the throughput. That is correct. But for the GenStore NM, if you take a look at the paper, it would still require that small DRAM inside the SSD to assist with some random accesses and some smaller granularity of the data. But for the GenStore EM, I think that yes, it can be augmented with processing using flash too. Now that let's say the access patterns have been optimized for the scenario. Are there other questions? Can you have Mike?
It's rather an idea, not a question. So could you go to this slide about the sorted K-mer index, which contains the strong hash value for GenStore EM?
Let me go there.
So I think the strong hash value are integers or long that are strictly in increasing manner. So
no. So we use a fixed length. I'm just using it. I'm using it in here, but we use I forgot exactly how many bits, like 30 something bits, if I'm not wrong, 30 or like close to 40 bits. So yeah, the length is at least always the same.
Right, but my idea is that we can store the difference between the values instead of storing the exact value because they're increasing manner.
Yeah, that is true.
So yeah, I think the difference will be smaller than the 40 bits or so. Maybe you can just put it in a short or something, so that we can further reduce the size of the index and maybe allow say building index for larger databases, because now we have like 126 gigabytes for even a human genome. So yeah, it's a bit huge overhead, I guess.
Yeah, I mean, like with this hash values, gets divided almost by 4. So it gets smaller than that. But yes, you can use kind of like it's a compress it by using the deltas and then add every time. So that is true, yes. Yeah. Thanks.
Okay, thanks, Nika. I think we can, yeah. I think we can move on. Yeah, I think we can move on to the next talk. And people, if they have questions, they can certainly ask you later and read the paper. We may be able to, and there's a lot of opportunity in this direction, certainly. And looks like people are developing ideas also to improve the storage overhead, which is also quite good. So I would encourage people to think about more things that can be done in storage, as well as using analog computation capability and also accelerating other genomic workloads going into the future using storage. Okay, great. Now next up is Joel. We'll probably run over a little bit, but if people need to leave, feel free to leave. Otherwise, feel free to stay and listen to Joel's talk until completion. Joel is going to describe SeGraM, which is the first hardware accelerator for genomic sequence-to-graph mapping, which can also do sequence-to-sequence mapping. This was published in ISCA this year in 2022. It's part of the PhD thesis of Damla, who was my PhD student. She graduated from Carnegie Mellon last year, and Joel is heavily involved in this work. So he's going to give the talk. Joel is a PhD student in my group. He's working on genomics and DRAM and acceleration. Joel, please go ahead.
Yeah, thanks. Great. All right. Okay, great. So yeah, I'm presenting to you this SeGraM work. Thanks for the introduction, by the way. This SeGraM work was led by Damla, who's now working at BioNano Genomics. So she's doing this for a job now. So I guess should speak for the quality of this. So I'm starting with a quick introduction, overview of the work, and then we're going to go more in depth and looking at the details. So recall that sequencing enables us to determine the DNA contents of an organism's genome. And this gives us many interesting types of information. So we can use it for personalized medicine, for outbreak tracing, and for understanding evolution. Now, when we do sequencing, we somehow get a physical sample, we put it into a sequencing machine, and out we get a randomized fragment of the genome, which we call reads, so many randomized fragments. And depending on the sequencing technology, and depending on the company that manufactured the machine, what you will get out is short or long fragments there, so short or long reads. This could be anywhere from a few hundred base pairs or characters long up to thousands or millions even. And then, well, you get different properties like different error rates, for example. So when we get these reads that are a bit noisy and randomized fragments, we need to do computational analysis steps. And like Nika showed, I'm trying to go quick here. Like Nika showed, actually Nika focused on this one, the linear reference genome, where you have one reference and then you try to match reads to it. Right? So notably, however, this linear reference genome fails to account for variations in a population. So humans are different, for example, and not every human's genome is the same. So one linear reference genome fails to capture all of this. What we look at in this work is a graph-based reference. So this graph-based reference tries to kind of unify all known variations across the population, and then we try to map to this graph. Mapping to this graph, which contains all known variations, notably improves accuracy, but it's a more difficult computational problem. So graphs are a bit more irregular than just a sequence. And yeah, it turns out this is a strict superset of this linear mapping problem. And because of that, there's no prior hardware accelerator design, well, prior to this work, that is. So our goal was to build a specialized, what is an enumeration there, specialized high performance, scalable, and low cost algorithm hardware co-design. And we wanted to actually accelerate multiple steps in this pipeline. So we didn't just focus on one piece in the steps. So we proposed SeGraM, the first universal algorithm hardware co-designed genomic mapping accelerator. And interesting here is that we call it universal because we kind of support many things. So we support sequence to graph mapping. We support sequence to sequence mapping, so the classical one. And then we support both short and long reads, which is also not common for these accelerators. So we try to do as much as possible in one accelerator. And then we get, for all of these use cases, we kind of get, good performance. So you can see between 5 or 100x speedups, and then good energy efficiency. So we use between 4 or 3x less power. This is against software baselines. And then, well, against some software baselines, we get 40 to 500x speedups. And then even against prior hardware accelerators, which were for sequence-to-sequence mapping only, we also get good speedups. So that's the overview of the work. Let's go into some details about these graphs. So you had some introductory lecture by Mohammed Alsar about genomics. And he showed you some, for read mapping, I think he showed you some picture of a rhino and a puzzle game with a picture of a rhino. Not sure if you recall. I'm trying to reproduce that here and then from that motivate why we want to do genome graphs. So really when we work with genome data, it's text, right? This text of ACGT characters, it's a long string. So for a human, this would be many as 3 billion characters. So if you use 1 byte per character, that's 3 gigabytes for a single human. I'm visualizing this string that you actually get here as a picture, as we discussed. And the reason I'm visualizing here as a picture, because it determines features of a human here. So in the picture, you can see the guy's eye color, which is brown, I think, the shape of his face, and things you also cannot see on the picture, such as allergies he might have, or if he's responding very well to a specific medicine, if you give it to him, for example. So that's unfortunate. Okay, there we go. So I'm going to this abstraction of the picture for the moment. And then if the full genome is the entire picture, then the reads are fragments of this picture. Yeah, recall the rhino example, same thing here. And the task of read mapping is to rearrange. Now, pay attention, rearrange, no. Okay, rearrange these into such that they make sense. So if I'm going back, we get them in some randomized garbled form. We rearrange them such that they make sense according to this reference genome. So these reads, again, can be short or long, but the key point is their locations are unknown, and in mapping, we try to recover them. Here, I'm showing sequence-to-sequence mapping. That is one single reference genome, and we try to, according to this single reference genome, we try to recover the locations. There's a bunch of prior works that does this. So by now, we kind of understand well how to compute this, how to accelerate the computation of this. So what you will find also is several works from our group in here, notably Genome, this recent one here, and the one that I led on the bottom right there. Well, still needs to be published. But the point is we understand how to do this sequence-to-sequence mapping fairly well. The problem is, well, we'll get to the problem. I changed something in the puzzle here. So look closely at the puzzle pieces. Does anyone notice the thing I changed there? Yes, thanks. Certain pieces there are colored. What we like to call them in this context is variants, right? Or reads from a location where the variant is in the genome. So crucially, somehow we got reads from a person with purple skin. And if we want to map this, well, for some of these, it might still work, right? So here the guy has purple hands, but we can still map it because we kind of have enough context still that's unmodified. So part of his sleeve is still there, part of the vacuum pipe is still there, and they can deal with this purple hand fairly well. So for some of them it works, but for many of them, there's just not enough context anymore. So if most of your read here is just purple now, you have no idea where this belongs to in the original picture. And we call this reference bias. So basically, we're particularly good at mapping exactly the things we already know in our reference genome, and we're particularly bad at mapping things that we don't know in our reference genome. Unfortunate thing here is that the part that's not in our reference genome tends to be the interesting part, right? So when I have some variant that's kind of unique to me, maybe I'm allergic to something, that's really the part that I'm very, very interested in mapping correctly. And the parts where I'm just the standard human, well, maybe I'm not that interested in. So we're really annoyed about this reference bias. And a first solution could be to just take all reference genomes that you may know of. Right? You have 4 here in the world. We have 8 billion humans. So if you map individually to each of 8 billion reference genomes, you might get an 8 billion X slowdown, which maybe is not so desirable, but maybe it could do the job. The solution 2 here that's much more exciting recently is this graph-based reference. So you start with one standard human, if you will, and then in a graph representation, you only store in addition basically the variants that you know of. So maybe there's this kind of face with big eyes, happy face, and purple guy face, and same thing for the hands. But the point is we didn't keep a lot of redundant data, so all the white space here we only stored once, his shirt and the vacuum we only stored once, and when we do mapping, we also don't map to redundant data all the time. So that's why we want to work with genome graphs. It's a long introduction, but I think a useful one if you got into the intuition up to here. Okay, we went through this text. I'm just wanting to show you how this actually looks, this genome graph, when we're going back to text representation. So we're starting with some standard human here, for example. This turns into one graph node. Now we are adding a second reference genome, which we see, okay, it differs only in one character. So we kind of try to build a graph that has, we split it in half because these parts are equal, right? So these 2 big nodes remain. And then we have alternate paths that each represent one option for a reference genome. Now we add a third sequence, and okay, it gives us kind of one more pass just to capture this small variation, and a fourth sequence that captures another possible variation. But the point is this single reference graph now captures the entire genetic variety of all these reference genomes. So we have our graphs now. How do we map to them? Mapping to a graph looks fairly similar to mapping to a sequence. So we start with some pre-processing steps. We construct some genome graph, and we construct an index. And both of these can be offline pre-processing steps. So you compute these ones, throw them to storage or RAM, and then they don't really count to your runtime, basically. Then during your runtime, you have these 3 steps down here. So seeding, filtering, chaining, clustering, and sequence alignment. So, okay, I already showed this. This is the offline step. Now during runtime, so here's where you get your runtime. Here's where you get your reads during runtime. You send them to the seeding step. And what the seeding step does is essentially using the index to find candidate locations. I think Nika showed this to some extent. This still looks fairly similar to the sequence-to-sequence mapping use case. The only difference here is that when you find basically one potential matching location, you get out one sequence and a small subgraph of the larger graph instead of a substring. Then you pass this candidate mapping location through some filter maybe to optimize performance. And finally, you go to a fairly expensive sequence to graph alignment step. And out of the sequence to graph alignment step, you get the optimal alignment between the read and the subgraph. This last step is really the most crucial one. All the other ones are really analogous to sequence mapping. But this last and typically most expensive step is the crucial one, so sequence to graph alignment. So we should look at this key part of the accelerator. So in classical sequence-to-sequence alignment, you have on the left some query read, and on the top you have some linear reference genome, and you need to fill this table. So if this is a table of numbers that you need to compute, don't worry about the details, but basically each cell that you compute, you will look at 3 neighbor values, you do some small computation and fill the next cell. This is nice and well, regular for a hardware accelerator because passing values from, for example, a neighbor processing element is kind of, well, convenient, right? I can always, just giving a value to my direct neighbor is typically easy. It's probably can be implemented well in Verilog, for example. Now, if you have a graph-based reference, the query read stays the same on the left, but on the top, we might all of a sudden get these kind of shortcuts. We call them hops in this context. So yeah, you have shortcuts in your graph, right? So you're, well, plotting them here at the top also. The problem is if you want to now compute the green cell, then you not only have to look at the 3 direct neighboring elements, but also whatever the source of that hop is. So it starts to get kind of irregular. Computer scientists are happy to work with graphs, but implementing this as a hardware accelerator will get kind of annoying because, well, how do you do the deal with this irregularity now? How do you get the, several columns ago computed element? So that's a key part of the accelerator that we will look at. Okay. So there are several state-of-the-art software tools that have figured out how to implement this algorithm somewhat reasonably on a CPU. And what we get out of there is that alignment is still a bottleneck, even in the sequence-to-graph mapping use case. So we really want to accelerate this table calculation, among other things. Then you suffer from high cache miss rates, so you would like to keep this near memory if possible. And same thing for seeding. It suffers from a DRAM latency bottleneck. So again, you would like to keep this near memory. That's why we're designing a PIM accelerator here. And finally, these tools don't scale very well to longer sequences. On the hardware side, we observed that these sequence-to-sequence mapping accelerators that I claimed are well studied, they don't generalize to graphs. You can't just throw a graph at them and they just work. And then, well, there's other graph applications, right? There's many graph applications that computer scientists work with, but somehow you cannot just take any of these accelerators and also throw this graph at it, and it just works. We really need to design a new thing. Finally, let's get to SeGraM. So we proposed this first universal genomic mapping accelerator, and critically, we support both sequence-to-graph mapping, this new use case, the sequence-to-sequence mapping use case, the old one, and we do it for both short and long reads. We design it by doing a algorithm hardware co-design, and we basically implement 2 algorithms. So we implement 2 components, a minimizer-based seeding algorithm. This is not the alignment step, but the seeding step that comes just before. And then we develop a new bit vector-based alignment algorithm that does the heavy lifting. So that's our algorithm side. And then we co-design these algorithms with an efficient hardware implementation. So really, we go back and forth, kind of, do we have an efficient algorithm? Let's try to efficiently implement it. Okay, we got some implementation. Can we somehow play with our algorithm to make it easier or nicer to implement? And that's what we came up with. Okay, so many boxes. Let's go over them. So there's 2 main components. On the left, you have min-seed in purple. And then on the right, we have bit align. Yeah? So left one does the minimizer seeding algorithm. The right one does the pairwise alignment or sequence-to-graph alignment algorithm. Then these are attached to some main memory. So here, HBM. And then they get inputs from a host CPU. So now I'll be showing you kind of a data flow through here. So we have some host CPU that's responsible for like pre-computing our graph and index, preparing it nicely in HBM. And now we get, well, some data passed through this accelerator. So if you bear with me, I'll animate through here. yeah, so a bunch of steps there. It does a nice circle through the accelerator and comes back eventually. We start with reads. We somehow pull them through our minimizer algorithm to find basically short substrings that we try to match exactly in our hash table. Then we find candidate locations from that. So places in the reference graph that might map particularly well. And then we evaluate each of these locations in our sequence to graph alignment accelerator. Yeah, okay, so let's look at these two components in some detail. So the minimizer-based seeding step consists of some compute steps and then some scratch pads in between. So let's see. The compute module is very simple logic. Yeah, we don't have to go over minimizer computation, but you do basically you take some, it's almost no computation that you briefly look at the data, you make some determination which substring you take, and then you're done. Then we add some scratch pads in there. So it's SeGraM basically. And surprisingly, actually, this is quite of the equal size almost as the computational part. And then we attach it to HBM memory. So this, it turns out, I showed this is a DRAM latency bottleneck if you do this on a CPU, right? So here we have it tightly integrated with HBM. So we are very close to HBM to have low latency, and we also get high bandwidth. Then from that step, we got out some candidate subgraph or a bunch of candidate subgraphs for a read. And then we evaluate this using a linear systolic array-based accelerator. So this is a convenient technique because it kind of captures well, you have processing elements here, and it kind of captures well this idea of I compute some small value, I pass it on to my neighbor. So if I recall, I said, this is the easy part, right? Computing something, passing the value directly onto your direct neighbor. That's easy to do. And okay, you also store some of your computation. So, well, it's easy to do. We also had to figure out how to do that well. That's some prior work, basically the direct predecessor to this work, where we came up with some really nice, efficient algorithm to do this for sequence pairs. But what we're missing is getting data from your non-direct neighbor nodes, right? So that's the key part that's added in this new design. And it's done with these hop-queue registers. So what each of these hop-queue registers tracks is it kind of keeps the most recent n values you have computed. Keeps all of your n most recent values you computed, and then at a later point, when you need your non-neighbor values, you go look in these hop-queue registers. You see, okay, I need the 10th oldest value, give it to me, and you keep computing with this. So we managed to generalize our algorithm to some fairly efficient hardware implementation, and it still works all nicely together. How are we doing time-wise? Let's see. Okay. So we integrated this. So we have the host system that's responsible for some pre-computation stuff and giving us the input reads. And then our computation module is tightly integrated with HBM. So it's in the logic layer of HBM. So essentially you can very closely pass data from HBM to your compute module. And each HBM channel within a stack is attached to a SeGraM accelerator, which consists of a min-seed module and the bit align module that I just showed. And then we just kind of data parallel manner scale this up. So we have several channels in stack 8 here. So we, in a data parallel manner, we can work on many strings in parallel. And then we have multiple such HBM stacks. So now we get 8 channels times 4, 32 accelerators for the full SeGraM design. Okay. What's convenient about these two sub-accelerators is that we can disable and enable them individually. So for the full sequence to graph mapping use case, we're using both accelerators, but now we can consider disabling one of the two. And then we enable other use cases. So if we disable seeding, we can provide just sequence to graph alignment instead of full mapping. If we disable, okay, we can also just provide sequence to sequence alignment if we disable the seeding. And finally, we can just also provide the seeding accelerator by disabling the second one. So we kind of you can do 4 things with one accelerator by just disabling one thing. That's nice. So we evaluated, we had got all this nice general accelerator now, and we evaluated, of course, how energy efficient and high performance and area efficient we got this to work. So we synthesized our design with Verilog. This gives us kind of area and power estimates. And then we compare this to software baselines and some prior hardware accelerators, and then some standard genome graph data set for comparison. Okay, our synthesis gives us kind of area and power breakdown. You don't have to go over the detailed numbers. The key point here is that somehow for the total accelerator design, we need in total something like 27 millimeters square of silicon area on some very large process node. So as compared to a full CPU, this is much, much smaller. And we only need 24 watts. So a regular desktop CPU also draws more than 24 watts. So we're already kind of area and power efficient. And when we look at actually how we're now spending our power and area, it's interestingly both in scratch pads and in compute steps in equal parts. So even in a PIM accelerator, the memory again is fairly expensive compared to computation. Even if you're doing processing in memory, the computation is only half of your chip area and power. So we got area and power that look kind of reasonable. That's compared to these software tools. We see on average, compared to these 2 software baselines, we get something like 5.9 and 3.9x throughput improvements, and also not shown here 4.1 to 4.4x energy efficiency, or this power improvement. So that was for long reads, and then for short reads, we actually get even more significant gains. So 100 to 700x performance improvement and similar power reduction. So that was for mapping use case. Now we take a software tool for only the alignment use case, and again we see it's really, really beneficial. So our design, our algorithm hardware co-design worked out really well. Well, then we look at this sequence-to-sequence alignment. So recall that sequence-to-sequence alignment, the old use case, which I claimed is well understood, there were already accelerators for this. So we went back and compared to these accelerators that could only do this, and checked how efficient we still are. Unfortunately, these extra functionality that we provide, the sequence-to-graph alignment, means some of our hardware is unused. So these new hop queue registers that we integrated to deal with these non-direct neighbors, they're unused if you do sequence-to-sequence alignment, but they don't actually cause us throughput overhead. They cost us power and area, but your throughput is actually not affected. And that's why we beat even these prior state-of-the-art sequence-to-sequence accelerators by quite handily. But unfortunately, this comes at, as I said, at power and area overheads. And same thing for short reads. We also beat the prior state-of-the-art there. Okay, so we have many more. Well, it's of course the paper is much more in depth. We went through many nice algorithm details in the paper, and how that relates to the prior GenStore work, and how we basically minimally have to modify that to provide this new use case. We go into a detailed evaluation methodology with accuracy, and also figure out where we got our improvements from. In the end, we proposed SeGraM with these different use cases. It's very general. It supports both short and long reads. It consists of these 2 accelerators, MinSeed and SplitAlign. And well, I already said that. And finally, we saw that it outperforms state-of-the-art software solutions for this new use case, but also state-of-the-art sequence-to-sequence solutions for this older use case. So it wins all across the board, I guess. if you're interested, please check out our full paper that we had presented at ISCA. And currently, we also now have all our code on GitHub, so you can play with the algorithm. Well, the software emulation of that same algorithm, I guess. But even on CPU, I guess it's not too bad. So you can play with it and see how sequences are aligned. With that, thanks for your attention. And if you have any questions, I guess, yeah.
Any question?
Please.
In your picture, you show like a tight integration with each VM.
Yes.
You see, right? Can you instead of a tight integration, you move the from logic.
This is in the logical layer. Sorry if I misled you there. This is in the logical layer, yes.
Oh, okay.
Yes, maybe I shouldn't have said tight integration. Yes, it's in the logic layer.
Okay, thank you. Any other question? Then I think we are done. Thanks a lot, Joel, and also previous presenter. See you all next week. Have a nice weekend.